our next speaker is Yuval Kochman. Yuval is a professor at Hebrew University. And what is going to be your talk, Yuval?
Explaining the optimality of Dolinar's receiver for BPSK over optical channels. Okay,
so those who are interested in optical channel will have a very interesting talk, right? And also, it's from information theory perspective?
It's somewhat connected.
Okay.
Yeah, so this talk will be, I guess, very different from Ido's talk and from previous ones. I'm basically using the fact that Chaim told me to choose what I want to talk about. And this is something that I'm excited about lately. So let me see. Okay, screen is okay?
Yes.
Okay. So this is joint work with my student Kamal. And basically, we're interested in the following problem. So say that you have, that you transmit over an optical channel, you transmit BPSK, that is one of two possible states, where these states are coherent states. And the coherent optical state is what you get. It's a good model for what you get at the output of a laser, for example. This state is characterized by a complex number. Let's call it S. So this S includes amplitude and phase. And it's very convenient to work with because when you send this over a free space optical channel, then also the channel output is a coherent state. All you get is some attenuation, right? So you send S, you're going to get gamma S, where gamma is smaller than 1. Okay, and it will turn out that the complex values are not really necessary for our talk. We can assume that we have two values, S0, S1, which are reals. Now you can ask, okay, I'm sending a number S. All the channel does is attenuates the number, so I can, without loss of generality, think that just I'm creating some S at the channel output. So this is a clean channel, right? There is no noise, nothing. So why is there a problem? Why is the rate limited? So the thing is, I cannot measure this S directly. Quantum theory limits the operations that I can do, the measurements that I can take. And there are various possible measurements. The one that is simplest to do is to do what's called direct detection or photon counting. So I'm just putting a detector that counts number of photons that it observes. But given S, this is not deterministic. This is a Poisson random variable with mean that is the squared absolute value of S. Right? So I have only a measurement of energy, not of the phase, and also that measurement is stochastic. I could also measure the phase, but if I measured the phase, then I would have a less accurate measurement of the amplitude. These are the laws of uncertainty. But again, this is the simplest measurement, and this is what people usually do. Okay, so there's a problem here because say that I transmitted either plus S or minus S, right? This is like a normal BPSK constellation. And I feed this to a photon counter, then I'm going to get the same Poisson measurement, and there is no way to distinguish between the two. Kennedy, we're talking now, I think, late 60s or early 70s, proposed the following. He said, why don't you add a local signal So that means I have a local coherent state that I add to the received state. So this is L. And then I get either S0 plus L or S1 plus L, and then I feed it to the photon counter. So for example, I can take L equals S, and then minus S plus S becomes 0 or 2S, and between these two, I can already distinguish using a photon counter. Of course, I could transmit 0 and 2S in the first place, but transmitting plus minus S is more energy efficient. So this is one use of the local signal. The other use is if I have a very strong prior, let's say I think it's going to be 0 with probability 0.99. Then I can get more information. I'm saying this now in a loose sense. We'll see this later. I can get more information using this bias. Basically, if I'm almost sure that this, let's say that I'm sending -1, then I will want to add 1, and then under this hypothesis, under this likely hypothesis, I'm feeding 0 to the counter, and I'm not seeing any photons. So if I do see a photon, then I have a big surprise. Then I know that I'm wrong. So this is this turns out to be a very informative measurement. Okay, now we're getting to Dolinar's receiver. So Dolinar, in his PhD thesis, he was a student of Kennedy. He said the following: if I can already add this local state, then why don't I make the local state dependent on past measurements? So I have this feedback loop. S of t comes in, then L of t joins, and this goes to the counter. The counter output is N of t. These are counts with Poisson rate lambda of t. These counts go to the controller. And this controller, based on the history of N of t up to this current moment, can decide on the new L of t in a causal manner. And it also outputs, let's call pi 0 of t. This will be the posterior probability of 0 based on all of the measurements up to now. Okay, and lambda of t is, of course, S plus L absolute value squared. Now, our goal is to design L of t in an optimal way. What is an optimal way? We want to minimize some function f of the posterior. For example, if we're interested in error probability, then of course the detector is going to say 0 if pi 0 is greater than 1/2. So the error probability is the minimum between pi and 1 minus pi, right? So this is the function that I want to minimize. He also solved this. He gave the optimal design for L of t for minimal error probability. And this is really cool, really surprising. So there are closed form expressions for two functions, L0 of t and L1 of t. I can pre-design them. These two functions are only functions of the prior pi 0, the prior that I have on my constellation, and on the two waveforms I want to distinguish between S0 and S1. And then I have formulas. I have this L0 and L1. And what is my local signal? I start with one of them. And let's say at this moment, I saw a photon. So I'm jumping to the other one, and so on and so forth. Every time I see a photon, I switch between these two pre-designed waveforms. And we have a closed form expression for the error probability using this detector. So it's easier to express not as a function of error probability times 1 minus error probability. So this is the initial value of the same quantity times some term that decays exponentially. And the exponent is the integral over time of the square difference between the waveform. Okay, so there are a few miracles here. One miracle that I'm not going to try to explain is that this system achieves the minimum error probability that is achievable by any quantum measurement. So say you had all of the equipment that can be built in the universe, and not just this local oscillator and photon detector, you could still not get a lower error probability. But what I want to explain is more classical. So let's even say that we limit ourselves to this architecture. Why is there a closed form solution? Notice that this solution is independent of the time horizon. So if the detector wants to output a decision after 1 second or after 2 seconds, still the optimal policy for the first second is the same. And it turns out that this same solution is also optimal if I wanted to maximize mutual information. So if I took my function to be the binary entropy of the posterior, of course, the mutual information is the binary entropy of the prior minus that of the posterior. So minimizing the binary entropy is maximizing mutual information. So the same policy also maximizes mutual information. So if I'm now going to send multiple pulses and I want to put some classical code over these symbols, then still per symbol, the best detector I could use is Dolinar's receiver. This is not the case, right? I mean, of course, it's trivial if the prior is 1/2. But if the prior is not 1/2, then of course minimizing uncoded there and maximizing mutual information is not the same. But it turns out that in this case, the same receiver optimizes both. About 10 years ago, there were 2 attempts of 2 groups, one of friends from MIT and the other one, a group from JPL, which included Dolinar himself, to try to explain this from a more information theoretic point of view, especially explain why the same detector works for both uncoded and coded. What they did is nice, but I don't think that it fully explains what happens. So here's a partial attempt that we're doing now to explain. Okay, so what can you do with this problem? You can talk about small time intervals. So instead of talking about continuous time, now let's talk about very short time epochs, let's say of length delta, where delta is small, and say that I design the local signal per each time period, right? It stays fixed over each short time. And if the time is very short, then actually I get a binary channel, because in this short period, the Poisson process is not going to give me 2 counts. I'm going to have, most likely, I'm going to have 0 counts with some probability that's proportional to delta. I will have 1 count, but 2 counts onwards, this is already order of delta squared. This is not going to happen. So now I have a binary channel. The input is x, which is either 0 or 1, with prior pi 0 and pi 1. Now here, these pi 0 and pi 1, these priors, if I'm now in the middle of detection, these are the posteriors that I have based on my past measurements. And why the channel output, why 0 if there was no photon, why it was 1 if there was a photon. So the probability of a photon given x equals 0 is lambda 0 times delta, where lambda 0 is S0 plus L squared. So I can, now I control L. So by controlling L, I can choose which asymmetric binary channel of these, out of this family of channels, I'm going to observe at each time instant. And usually in these situations, I have some trade-off between exploitation and exploration, right? Exploitation, so I want to maximize the reduction or the expected reduction of my error probability or whatever I want to optimize during that time. So I define delta f. This is the function f before, the function f of the prior, minus the expected function given the measurement, so the expected function of the procedure, and I divide that by delta and take the limit of as delta goes to 0, right? Because I want to see the improvement over a very short period of time. So this is what I would like to do. But in general, of course, there is the question of exploration, right? Maybe I could give up I would see less improvement currently, but this will build the future. Of course, since we know that the solution is independent of the time horizon, we know that actually we don't need to explore. But in general, we won't. Okay, so I want to optimize this. So this is just the binary channel.
Can I?
Sorry, I guess this was unintended.
Yes.
So this is just a binary channel, so I can write the posterior probabilities and so on, and I can write an expression for the expected improvement in my function. This is something that's proportional to lambda bar, which is the expected photon rate that I'll get. And here I have two terms. One is, okay, pi n is going to be the new prior that replaces pi 0 if I'm really surprised. So if I did get a photon, which happens with low probability, with probability that's proportional to delta. And this second term, this is the local improvement. So this is the change in the function if I was not surprised. If what happened was what's going to happen with probability almost 1, that is, there is no photon. So there is a trade-off between these two, and you can optimize over L, right? Because L, the local signal sets the rates, thus it sets this lambda bar and sets pi n. So you do this explicitly, and you find it's easy to do for error probability. You find the following. You have some optimal L, and what happens with this L is that pi n equals 1 minus pi 0. Now, this is really special. So this means that actually, if I see a photon, then all that happens is that pi 0 and pi 1 switch roles. If before the photon I was 80% sure that it's 0, then after the photon I'm 80% sure that it's 1. This is what happens using this optimal measurement. Now, since this is what happened, then photon arrivals don't change the error probability at all, right? Because it was in the example that I gave, my error probability was 0.2 before, and it is also 0.2 after. So the probability that I'm going to decide wrong, if I have to decide in a symbol, is the same no matter what were the measurements that I saw, right? So this is why using this solution I can design anything in advance, right? Because I'm up to a sign, up to which one is going to be the more probable symbol. I know in advance what's going to be the probability assignment. I know that after 1 second, for sure, I'm going to have 0.7 and 0.3. I just don't know who's going to be the 0.7, who's going to be the 0.3. That depends if I saw an even or an odd number of photons up to that point. So this is why I have these two functions that I alternate between. Let me just say the following. So so here is just an expression for the optimal local signal. What's interesting about it is if I take the limit of this as pi0 goes to 1, so this optimum really becomes minus S0. So this is what I said before. If I'm almost sure that I'm going to see a certain signal, then the best I can do is try to cancel it and have 0 photons, and then be really surprised if I see a photon. And also, if you look at the average photon rates, then this average is proportional to pi0, pi1 over the difference squared. So when either pi0, pi1, sorry, go to 1, this rate goes to 0. So as I'm measuring, as I keep measuring with time, my probability to see another photon keeps diminishing. Okay, so that was for error probability. But why do I get the same if I'm interested in mutual information? So here is what we have. Let's say, up to now I was talking about the error probability function, which is the minimum between pi and 1 minus pi. Now I'm saying let's replace it with any function f of pi which satisfies the following. First, this is a function that is symmetric around pi equals 1/2. So my objective remains the same if I flip between the two probabilities, which makes sense for lots of objectives. And second, I want it to be a concave function, but not too concave. And let me explain what not too concave means. So this has to do with the notion of relative convexity, which appears, for example, in a paper of Palomar from 2003. We say that a function is convex relative to another function if at any point, at any value, I normalize the two functions such that they will have the same value and same derivative. So, for example, I take one of them and I shift it until I shift both until they both have 0 value, and then I also scale them until they have the same slope. So now the functions are tangent one to the other, and then I say one of them remains above the other always. So this is relative convexity. For example, of course, this reduces, convex means relative convexity relative to a linear function. So what I'm saying here is that my objective has to be more convex than square root of pi times 1 minus pi. So there are many functions which are in terms of this relative convexity between the error probability function and the square root function. For example, the binary entropy function is one of these. So that's why binary entropy also is minimized by the same. Okay, I'll finish by saying that there is still a gap. So we took this greedy solution, the solution that tries to optimize at each time instant the reduction in the function, and we saw that this solution has very nice properties. One property is the error probability is independent of the measurement, so I can pre-design everything. And second is that the same greedy solution also holds for mutual information. but we didn't say that this greedy solution is optimal. We didn't see that you shouldn't explore, that you shouldn't try something else at any time instant. We do know that it happens because of the Hellstrom bound, because we know that no quantum measurement can do better, and if no quantum measurement can do better, then in particular, no measurement of this form can do better. But this is like a Deus ex machina. This doesn't come from any optimization considerations. This is really something quantum that is outside the scope of what we discussed. So it's not very satisfying. We would like a direct proof of that. We still don't have one. The good news is that if we prove this for error probability, it will immediately extend for all of the other objectives. For example, to mutual information, because the error probability function is piecewise linear, and the other ones are concave, and concavity works in the right direction. So once we prove this for error probability, we will also be able to prove that this is indeed globally optimal for mutual information. Okay, so unlike Ido, I didn't get any questions. So if someone is still with me and would like to ask something, please do.
First, thank you very much, Yuval. And is there any question?
I'm not sure how do I stop the screen sharing.
Okay, so let's have a 5 minutes break, okay? And after the 5 minutes break, Dolinar will chair the session. Is it okay, Or?
Yeah, sure.
Thanks. And we're going to have Ziv Goldfeld, which I see is here, and also Oron Sabag. They both are going to give talks. So few minutes break, and we'll start at 6 p.m. Israel time.
Okay.
All right. Thank you very much, Yuval.